students, welcome to the questionnaire round of chemistry sessions. So I hope you all have revised the concepts of general organic chemistry very well, all the kinds of effects, the electron displacement effects that we have done, and all the kinds of questions. You must be having a lot of practice for those kind of effects to be applied on the questions. So today we are going to discuss the JEE main pattern exercises. We will be discussing questions related to the general organic chemistry. So let us just move on to the first very question. What do we have here? Yes. Now the question says the order of stability of the following carbocations. So what kind of carbocations we are given? See here, can you recognize this carbocation? This is allylic carbocation we have got. So what do we have over here is the allylic carbocation. That one is the allylic. Now if I move on to the number 2 carbocation, what is this carbocation? This is a general carbocation. It could be primary, secondary or tertiary. So here it is nothing but the primary carbocation. So this very carbocation is primary. And let's move on to the third part. The third part has what kind of a carbocation? A very interesting kind of a carbocation, that is, yes, we all are able to recognize this. This is the benzylic carbocation. So we have got benzylic carbocation. So the question says the order of the stability out of the 3. So you can clearly see that out of the 3, number 1 and number 3, that means the allylic and the benzylic are nothing but the resonance stabilized. So what do we have over here? Allylic and benzylic. These are nothing but resonance stabilized. That means what? That means we have got the answer but not complete answer. Here allylic is also resonance stabilized, benzylic is, but this one is not. So this would be the least one option. We want to have the order of the stability. So the most stable and the least stable. We have got the least stable over here. This is least stable. So I hope you all are able to recognize this very type of carbocations. Now I have got second one as the least. So out of the 4 options, there is only the one. That means this very option has got the second as the least. So the answer would be D. But let us just discuss out of allylic and benzylic, which one is the most stable. So the benzylic and allylic I have got. Benzylic has been stabilized by the entire benzene ring, whereas in the allylic I have got just one kind of resonance stabilization. That is what we have here. That will be the resonance stabilization over here. And in the case of benzylic, what do I have? I have got the stabilization, resonance stabilization in the entire ring. Through the entire ring we have got. That is how it is going to be. That means number 3, the stable one, the most stable one is the benzylic, second one is allylic, and finally the one with having no kind of resonance stabilization. So that is our answer. I hope you all are able to get this very well. So D is the option over here. So I hope you are through with the question. Let's move on to the next one. So what do I have over here? Let me just rub this off. Yes, again a stability kind of a question. Now it says that arrange the carbon ions. Now we have got carbon ions. So I need the arrangement of their stability, and you need to have, just focus upon the question, the decreasing stability order. What all do we have? So let me just expand the options which are given over here. I have got a tertiary carbon ion That is how we get a tertiary carbon ion, the number 1. And then the number 2 is CCl3 negative. That is how it is going to be. So in order to have the question right, particularly in GOC, you need to expand the structures first of all in order to actually check whether the stability is there or not. So that is how I hope you are all following up. So I have got the secondary. Here this was the tertiary carbon ion. I have got a secondary as well. So we already have discussed the stability of carbon ions. So we will be using that fact over here. And the last one, what do we have? That is benzyl carbon ion, not the carbocation but benzyl carbon ion we have got. So that is somehow like this. Now, what is the answer here in this case? So I need the stability. I need the stability, which is the most stable one. First of all, I need to judge that. So for that, I need to expand it into a phenyl ring. Again, what comes up? The resonance stabilization, definitely. So that is a resonance. And what about this very option? Chlorine has got minus I effect. Cl has got minus I effect. And I have got 3 chlorines over here, 3 Cls. That means a booster of minus I effect. That means the chlorine is withdrawing the negative charge. So it is withdrawing the negative charge towards itself. And what do we have over here? Here what do we have? It's a tertiary carbon ion. That means instead of withdrawing groups, what do I have? I have got releasing groups over here. So many releasing groups, making the structure very, very unstable. So that is unstable. In fact, the unstable most. And what do I have here? I have got 2 plus I effect showing groups. This is plus I effect, let me just mention over here. And this as well. So here I have got 3 groups showing the plus I effect, 3. And over here I have got 2 groups showing the plus I effect. Now I need to have a stability. How to judge the carbon ion stability? In which the negative charge is dispersed very well, or it is able to hold the negative charge. So basically, how to judge the carbon ion stability? The one having the negative charge stabilization. So negative charge stabilization is the answer. So you must be thinking that the one having the resonance stabilization over here is the answer, but it is not so. If you look over here in this case, the 3 chlorines have got minus I effect. That means they are electron withdrawing. And what do you see over here? Just be very careful while observing all the options. The chlorine has got the d orbitals. It has got, let me just write it over here. Cl has got empty d orbitals. And whereas here if you see, these are all carbons, it has got only the p orbitals. So it has got the p orbitals over here. So in order to disperse the charge into the d orbitals, will be a more dispersal, more good dispersal, because d orbitals are always large in number, whereas the p orbitals have got less number as well as a smaller size, you can say. So the stabilization of the negative charge will be the highest here in this case. We are not considering these 2 cases. Why? Because these carbon ions are having, instead of withdrawing or stabilizing groups, but the donating groups. That means increasing the steric repulsions. So they have got high electron density. So that is what the reason is, not considering these options. So what do I have over here? Most resonance stabilization will be here whenever we have got the minus I effect. That means The most will be, yes, here we have got the answer, that is CCl3 followed by the resonance stabilization, that is obvious, and here we have got the secondary carbon ion. The stability of carbon ions follows the order. Carbon ion stability is actually primary is more stable than secondary than tertiary. So that is how the stability order is, opposite just to the carbocations. So I hope you all are able to follow this. So here what do we have? CCl3 followed by the benzyl carbon ion, then the secondary one, and finally the most unstable one, that is the tertiary one. So I hope you all have got the right answer over here. Let us just mark the answer. So I hope you all are able to do the questions very well and able to apply the logics. You need to have all the kinds of effects that you have studied so far to apply onto the questions. So that is how it goes. Let's move on to the next question. So let me just rub this off first. So let us start with the next question, a very simple question comparatively. So what do we have got here? We have got the reaction. Some kind of a reaction is given, that is a carbonyl group over here, and X is given. X could be anything. Now a nucleophile comes and attacks onto the carbonyl. So there would be some kind of electromeric effect that we have studied. And what happens here, whenever the nucleophile tries to get attached over here, the X will leave, finally giving the product. So I need to answer in which of the cases is the fastest will be the reaction. The fastest reaction will be in which of the cases? I am considering the values for X. What is the X group over here to make this reaction the fastest one? So that is the question. If the X leaves very, very easily and very quickly, what is there? Then the reaction will be the fastest. So we need to have, if X is a good leaving group, so we need to find a good leaving group. That means it leaves the vicinity quickly, and what will happen? The reaction will be the fastest. So therefore, fastest reaction. So that is how will be our approach. I need to find out a best leaving group out of the four. So which will be the best leaving group? So it's a very simple question. Just by looking onto the options, you can get the answer right. Here I've got OCOR, that is one leaving group. These are the groups that may be attached on here. I am representing this as a dash, that means these groups will be attached here. And if you see the sizes of the group, what is the property of a leaving group? If the size of the leaving group is bigger, it can disperse the charge very easily. That's what we have done in the category of leaving groups. So, bigger size, or I can say the large surface area. Large surface area, that means what? A better leaving group. So it would be a better leaving group. That means more charge dispersal, more negative charge dispersal. That is what the definition of the leaving group says. The leaving group is the one which takes up the electrons, so it will be somehow taking up the electrons and will be leaving the vicinity. So it need to actually hold on the electrons. So if it has got a room for that, a space for that, a bigger area, it will be holding the electrons very easily. So over here, chlorine has the biggest size, that is so obvious. So we have got the answer over here. So I hope you all have got this. Very, very easy question, but it applies a certain logic. Now let's move on to the next very question. What do I have? Yes. Again, we need to have now the nucleophilicity among the nucleophiles. A decreasing order here in this case. Let us just carefully look onto the nucleophiles that we are given over here. One is acetate ion, CH3O negative, cyanide ion, and this very ion over here having such kind of a group. So if you observe, what is a good nucleophile? Again, just like in the case of leaving group, a good nucleophile is the one which has maximum charge dispersal. So maximum charge dispersal, holding capacity you can say. It can hold on the negative charge very properly. So if it is resonance stabilized, then what will happen? Definitely the nucleophile will be having a better charge dispersal. So out of all, what do you see? Here we have got a resonance stabilization. Can I make the resonance structures? Definitely. That is how we are going to make the resonance structures over here. So I hope you all are able to make that. What will be the structure over here? O negative. That is what the resonance structure will be. That means a resonance stabilization. Can you see a resonance stabilization over here? No. Over here? Not at all. Over here? Yes, definitely. A very good resonance stabilization indeed. How? That is how it is going to be. Sulfur will be having now the positive charge. It could be fulfilled by this very oxygen, or the entire benzene ring can be involved in the resonance. So better resonance stabilization. Stabilization. So I hope you all are getting the idea. Now out of the two, or I can say out of the four, we take out these two as the best ones. And out of these two, the best one would be having more number of resonance structures over here. That means more resonance stabilization, more dispersion of the negative charge. So I hope you all have got the idea over here. So here the option D would be presented as the least. So I have got three options over here. I need to eliminate the possibilities now. So I have got 1, 2 and 3. What about the next one? The next one would be A, definitely. I am actually having a decreasing order over here. So just be very careful while selecting the options. You need not go for the increasing but a decreasing order. So that would be decreasing order of the nucleophilicity. So the maximum would be here. I am starting off with the least and going on to the maximum. So the maximum is D, having proper resonance stabilization. What else? A. So I have got two options. I eliminated this very group, this very option. That means D has been eliminated now. I have got A and B. Now let's move on to these two remaining options to actually find the answer. So over here, which one has the better charge dispersal is, if you have not got it, I can tell you the answer over here. This is the cyanide ion. Now can you see after expanding the structure, it is first of all sp hybridized first. It would attract the negative charge, it would hold on the negative charge properly. Also again nitrogen is what? Nitrogen is again an electronegative group. That means all in all it can be serving as a proper nucleophile, a good nucleophile, better than even this one, CH3O negative. So we have got the answer now, C, and the least one would be, that means the least nucleophilic character out of the four is of B. That means I eliminated the possibility A as well and I got my answer as B. So I hope you all have got the right answer as well. Let's move on to the next one. So let me just rub that off. What do I have over here? A pretty easy question but requires the knowledge of one very important concept that is related to aromaticity. So what the question says, which of the following molecules is least resonance stabilized? That means I need to check up whether there is resonance stabilization or not. If yes, which will be the least stable structure? So that is what we want to check. So what kind of important concept I was talking about here was the Huckel's rule. So Huckel rules, it says first of all it should be a planar molecule, planar. What else? It needs to be a cyclic one. What else? Number 3 is you need to follow the electron rule, that is 4n plus 2 pi electrons. So that is what Huckel rule says. Now let's apply the Huckel's rule on each of the molecules. What do I have here? In the first one, this is nothing but the benzene, properly resonance stabilized structure. That means first this is cyclic, second this is a planar one, we all know that, and the third is again following 4n plus 2 pi, that means in total of 1, 2, 3, 4 and 5, 6. I have got 6 electrons over here, so 6 pi electrons, that means it is perfectly aromatic. I have confirmed that this is aromatic. Now let's move on to this I have got what? Again, first is the cyclic, yes, that is cyclic, planar, definitely a planar one, and third is 4n plus 2 pi. So I need to include these 2 electrons over here in order to have a resonance. That is how the resonance is going on. And it will be 6 pi electrons over here again. So I have got 6 pi electrons, that means again a planar one, sorry, again an aromatic one. Let's move on to here. This is nothing but the pyridine. I hope you all have recognized it. So that is the pyridine. And pyridine is always an aromatic compound, again 6 pi electrons. I am not counting the electrons onto the nitrogen because they are out of the plane. So I hope you all remember the concept very well. This pyridine is actually aromatic, we all know that, again cyclic. I need not repeat all the 3 things. Again 6 pi electrons, so that means this is also an aromatic structure. Now let's move on to the option number D. So what do you see over here? I have got 6 pi electrons, this must be involved in the resonance. But what is the thing over here? Although it is cyclic, but that is not planar. Look very carefully over here. The condition for the planar is you need to have sp2 hybridized carbons or sp, but not sp3. sp3 has an entirely changed shape. That means changing the structure into the terms of geometry I am talking about, making it non-planar. So that is an sp3 hybridized carbon making the compound non-planar, violating the Huckel's rule, and also it will be now non-aromatic. So that is non-aromatic over here. That means out of the 4 molecules we have got the least one, which is least resonance stabilized, is number D option. So I hope you all have got the answer over here. Just try to analyze all the molecules over here and you will get the answer very well. So I hope you all have got this. Note this down, then I will be taking up the next question. So now let's move on to the next question. What do I have here? Let me just rub this off. A pretty simple question here we have got. I need to find out the most acidic hydrogen. How do we count off for the most acidity? That means which has been attached, the hydrogen that has been attached with the withdrawing group. So what do we have here? Let's draw the structures for each one of them. So I've got 3 hexanon, 6 carbon atoms, 3, that means onto the 3rd carbon atom. Let me just write it properly, having all the types of hydrogens present, CH3, CH2, CH2, CH2 and CH3. That is the number 1 option. Let's just quickly draw all of those. I've got 2,4-hexane dione. So just draw with me simultaneously. I've got 1, 2, 2, 4. So I need to have on to the second carbon the carbonyl 3 and 4, and again I need to make up 6. 1, 2, 3, 4, 5, 6. That's right. Let's move on to the next one. I've got again 2, and here this time I've got 5. That means ketonic group present on the 5. 1, 2, 3, 4, 5. Now I've got it right. And what is the last option over here? 2, 3. So that is how we are going to make it. So I hope you all have got the structures right. So we need to find out the most acidic hydrogen, that means which is most acidic one. Adjacent to, I need to first of all find out the alpha hydrogen which is attached onto the alpha carbon. So where are the alpha carbons? Most acidic would be the one which is attached with most of the withdrawing groups. So most acidic is attached to most or more number of withdrawing groups, more EWG. So here what are the EWGs? We have got the EWGs over here as these carbonyls, electron withdrawing groups. So it's very much evident. I hope you all have got what all are the acidic hydrogens, that means alpha carbons lying. Now the one which is attached with the most of the withdrawing groups. Here if you look in the first option, this one is attached with only one carbonyl as well as this one. Over here this one is attached with one carbonyl as well as two, that means very acidic. Over here these as well attached to only one carbonyls, as well as over here you can see these two are attached with one carbonyls each. That means what we have got? We have got the answer. This very will be the most acidic because it has been attached with the two withdrawing groups, making it more labile, making it more easily go off. That is what acidic hydrogen is whenever it goes off in the form of proton very easily. So I hope you all have got the answer over here. What is the answer? We have got the second option as the answer. So I hope that is clear to you. Let's now move on to the next one. So the next one over here says, let me just first rub that off. Now, a pretty easy question, but these kind of questions are repeated very frequently. Arrange the following compounds in the order of the decreasing acidity. That means I need to judge the acidity. How do we judge the acidity? In the structure where the hydrogen can be easily removed. That is how we are checking the acidity over here. So let's just observe the types of group present over here. If I've got a withdrawing group, it would be the most acidic structure because it will withdraw all the electron density from the benzene and the H plus can go off very easily. So over here, which one are the withdrawing? So here I have got first of all the chlorine. It is minus I effect showing. So chlorine is showing the minus I effect, withdrawing. This very group is showing what? Plus I effect, as well as the hyperconjugation. This very group again minus I effect, and over here again the plus I effect. So these two are showing the plus I effect, whereas these ones are showing the minus I effect. Also this group is showing plus R along with slight plus I. So I hope you all have got the answer by now. I've got 2 minus I. These two structures will be acidic out of the 4. Now I need to choose one. So over here if you see, whenever the NO2 is attached onto the benzene ring, it shows most prominently the plus R effect. Sorry, the minus R effect. since this is withdrawing, it will be showing minus R effect. So if you compare the two, NO2 and Cl, always remember this very thing, that minus I effect is always greater than the minus R effect. And it needs to be applied over here. I have got the answer over here. Which is most acidic is first one followed by the third one. That means I have got the option over here as, now arrange the following in the order of decreasing acidity. Least acidity would be in the case of these second one and the fourth one. So out of second and fourth, what would be having the most acidic, this or this? So naturally this is showing the plus R effect and this is showing the plus I effect. So it would be less, thereby making it more acidic. So 4, the least would be, we have got as second. So second is the least, then followed by, okay, now I have got the answer as, just need not go on to the options here. Friends, the answer would be the fourth one as the least and followed by, I have got the second one which is again showing the plus I effect. Next would be the most acidic I need to choose now. Out of NO2 and Cl, it would be the third one and highest would be the Cl. That is showing the minus I effect. And what do we have here? That is the first. So that is the answer over here. Need not go on to the options. The options may be showing the incorrect answers. So here what do I have? I've got the first, followed by the third, second and fourth. So I hope you all have got the answer here. Let us just move on to the next very question. So what is the next question saying? A solution of 1-chloro-1-phenyl-ethane in toluene racemizes slowly in the presence of small amount of SbCl5. So you might be thinking it's a very complicated question, but it is not. Why? Because here let us just try out 1-chloro-1-phenyl-ethane. I need to make it. So it would be 1-chloro-1-phenyl-ethane. So that is what we need to make, 1-chloro, 1-phenyl, and in total it would be ethane. Now I need this reaction in, first of all, that is the solvent over here used, toluene, in the presence of, with what I am reacting it? SbCl5. So it says we get a racemic mixture, it racemizes slowly. Racemic mixture means both the forms of enantiomers. So we have got D and L forms. So we might have studied, and definitely we have studied, the case whenever there is the chiral carbon and it actually racemizes into the enantiomers. So how do we obtain a chiral carbocation? So the reaction would be something like this. This chlorine will go off and we get a carbocation over here. That is the intermediate step that I am drawing over here. That is the intermediate step. This is nothing but a chiral carbocation, and that is the only intermediate species which will result in a racemic mixture. Pretty simple. You need not go on to the options to look for the answer, but you finally got the answer. This very thing, the racemization happens only in the case of formation of carbocation. So I hope you all have got the answer here, that is C. Now let's move on to the another one. What do I have? Again a pretty easy question. Order of the stability of the species again. So I need to stabilize the carbocations. Try to analyze the options a bit. So first of all, I would like to have either the carbocation is primary, secondary or tertiary. So that is our first approach. So over here if you can see, that is a tertiary carbocation. This very carbocation is secondary. Here what do I have? Secondary and primary. So naturally primary is the least. We have got the answer. That means number 4 is the least. So we have got 2 options over here, followed by number 2. Now number 2 are 2 options over here. Which is more stabilized, I need to check up. So here I have got a donating group. Also what do I have here? Very interesting thing. Oxygen having lone pairs, it will definitely be stabilizing the carbocation by resonance. So it would be more stable. That means more stable than second option. That means what do we have? We have got the second option over here, followed by the third, and the most stable carbocation will be the tertiary, definitely we know that. So we have got number 1. And finally, we have got the order. Super easy question. First approach would be the type of carbocation we have. Answer would be D here in this case. So I hope you all have got the idea. Let us just try out the very last question we have. Here, the most unlikely representation of resonance structures of para-nitrophenoxide ion. So what is para-nitrophenoxide ion? That is what it is. Phenoxide ion. You need to have a proper resonance structures, and what could be not the explanation, not the representation over here. So if you observe one by one, let's take out this very option. So if I actually shift these electrons over here, what do we get? Again the phenoxide ion having the double bond. That is how what we made over here. So I hope you all are following up. So this could not be the representation. I mean that this is a proper representation and this is not the answer. Next, we have got something like this. Now if you observe very carefully, the nitrogen, does it have its octet complete? So I have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 exceeding the octet. That means this case cannot be possible. This is exceeding the octet. So this cannot be the possible representation. It might be the answer. Let's move on to the C part. So as you can see over here, again this is a possible representation over here. It could be a representation. If I shift these very electrons, now the resonance starts within the phenoxide ion. That is what we have here. See here very carefully. The negative charge over here, positive here, and that is how the resonance starts into the para-nitrophenoxide ion. So this can be a possible representation. Now what about this? Again, that is a very particular resonance structure. In somewhere in the middle, I would be having such kind of a representation. That is, if there is a double bond over here, so this is also a resonance structure. Just try drawing the resonance structures for this and you will be getting one of the structures as this. So I hope you are clear with the idea, and what do we have over here? We have our answer. Here the nitrogen octet is actually exceeding. We have got 10 electrons over here in the octet, which is not at all possible. It cannot accommodate 10 electrons. That means B would be the most unlikely representation. Very unstable structure this is. So we are all through with the questions of JEE main exercises, and you must have noticed that this is not a rocket science over here going on. The JEE is not a big deal, but a very simple deal. Once you get the questions right, once you get the logics right, and you need to have your fundamentals clear to have the questions perfectly right. They are super easy questions. You just need to apply the logic and get the answer. Try to practice this at home, and I'll be taking up next series of questions in the next session. Till then, have a good day.